Deep inside the Sunday, there is an intense battle between gravity and energy. Gravity pulls the Sunday's mass inward, trying to make it collapse. At the same time, nuclear fusion pushes outward. This balance keeps the Sunday stable for billions of years. The Sunday's core, where fusion happens, has a temperature of about 15 million degrees Celsius. At this extreme heat, hydrogen atoms move so fast that they slam together and fuse into helium. When this happens, a small amount of mass turns into energy, as described by Einstein's equation, E=mc². This energy creates an outward pressure called radiation pressure, which pushes against gravity. Imagine a giant balloon. The air inside pushes outward, while the rubber skin pulls inward. If you add too much air, the balloon stretches and might pop. If you let air out, it collapses. The Sunday works in a similar way. If the core temperature rises, fusion speeds up. This creates more energy, which pushes the Sunday's layers outward. As the outer layers expand, the core cools slightly, slowing fusion down. If the core temperature drops, fusion slows, gravity wins for a moment, and the core compresses. The compression heats the core, making fusion speed up again. This natural feedback loop keeps the temperature steady. This process has worked for over 4.5 billion years and will continue for about 5 billion more. It is like a thermostat in your home. When the temperature gets too high, the thermostat turns off the heater. When it gets too low, the heater turns on. The Sunday's thermostat is the balance between fusion and gravity. The stability comes from how fusion reacts to changes. For example, if a small region in the core gets hotter than normal, fusion in that spot speeds up. It releases extra energy, which makes that region expand and cool down. Once it cools, fusion slows and balance returns. If a region gets cooler than normal, gravity squeezes it tighter, raising the temperature and increasing fusion. This constant adjustment prevents wild swings in temperature or size. Over time, the Sunday slowly changes as it uses up hydrogen fuel. Right now, it burns about 600 million tons of hydrogen every second. That may sound unstable, but the Sunday has so much hydrogen that this steady burn can go on for billions of years. In the far future, when most hydrogen in the core is gone, the balance will shift. The core will contract and heat up until it starts fusing helium. At that point, the Sunday will swell into a red giant. But for now, the balance between fusion and gravity keeps it steady. This quiet stability is why Earth has enjoyed a steady stream of light and heat for billions of years. It is the reason life has had the time to develop and grow without sudden changes in the Sunday's energy output. The Sunday's core acts like a perfect self-regulating engine, always making tiny adjustments to stay in balance. The Sunday's core is a place of extreme heat and pressure, but no one has ever seen it directly. Astronomers study it by looking at light and particles that escape from the surface. They use this information to build models of what is happening deep inside. These models show that hydrogen and helium make up almost everything in the core. About 3/4 of the Sunday's mass is hydrogen, and most of the rest is helium. A very small fraction, less than 2%, comes from heavier elements such as oxygen, carbon, neon, and iron. These are grouped under the term metals in astronomy, even though they are not all metals in the usual sense. The exact ratio of these elements is hard to pin down. Fusion in the core slowly changes the balance over time. At the start of the Sunday's life, hydrogen made up even more of the core than it does now. Over billions of years, hydrogen atoms fused into helium through the proton-proton chain, which is the main fusion process in stars like the Sunday. This steady conversion means the core now has a higher percentage of helium than the outer layers. Measuring this difference is difficult, because the core is hidden under hundreds of thousands of kilometers of plasma. Scientists rely on tools like helioseismology, which studies sound waves moving through the Sunday. These waves travel at different speeds, depending on the density and composition of the material they pass through. By measuring how the Sunday's surface vibrates, researchers can estimate what lies deeper inside. It is similar to how geologists study earthquakes to learn about the layers of the Earth. These measurements give a good idea of hydrogen and helium levels, but are less precise for heavier elements. Neutrinos, tiny particles produced by fusion, provide another clue. They escape directly from the core and travel through space almost without interacting with anything. By detecting these neutrinos on Earth, scientists can test their models of fusion and core composition. In the past, there was a puzzling mismatch between the number of neutrinos predicted and the number detected. This issue, called the solar neutrino problem, was solved when researchers discovered that neutrinos can change type as they travel. Even with this breakthrough, neutrino measurements still leave room for uncertainty in the exact ratios of elements. The amount of heavier elements in the Sunday, known as metallicity, remains debated. Some models suggest higher levels of oxygen and carbon, while others point to lower amounts. This disagreement affects calculations of how the Sunday evolved and how energy moves through it. For example, if the core has more heavy elements, it blocks energy flow slightly more, which changes how heat spreads outward. Consider a pot of soup with many ingredients. From the surface, you can guess what is inside by the taste or smell, but you cannot be certain of the exact amounts without stirring or sampling from deep below. The Sunday's core works the same way. Observations give strong hints, but the precise mix remains hidden, leaving scientists to refine their models piece by piece. Deep inside the Sunday, hydrogen atoms fuse into helium under extreme heat and pressure. This process releases energy that travels outward and eventually reaches Earth as sunlight. Scientists have studied this reaction for decades and built detailed models of how it should work. These models predict how fast hydrogen should fuse, how much energy should be produced, and how the Sunday's brightness should change over time. Yet, when researchers compare the predictions with observations, they find the Sunday burns more smoothly and steadily than expected. Fusion in the Sunday's core happens through the proton chain. In this chain, 4 hydrogen nuclei combine to form one helium nucleus, releasing energy in the form of light and neutrinos. The reaction depends on temperature and density. If the core gets slightly hotter, fusion speeds up, producing more energy. If it cools, fusion slows down. Models show that this balance should naturally lead to small fluctuations, with the core burning slightly faster or slower at times. But measurements of sunlight and neutrino output reveal very stable behavior, as if some hidden factor is keeping the process even and controlled. One way to picture this is to imagine a fire. If you add extra wood or air, the flames rise, and if you take some away, the fire dies down. The Sunday's core seems more like a campfire that stays the same size no matter what you do. This surprising stability suggests there may be feedback systems inside the Sunday that current models do not fully capture. Helioseismology provides clues. By studying vibrations on the Sunday's surface, scientists can infer conditions deep inside. These vibrations show patterns that hint at smoother energy flow than expected. It is possible that subtle interactions between particles, magnetic fields, or layers of plasma help even out the fusion rate. These effects are difficult to include in computer models because they depend on small-scale processes happening under extreme conditions. Neutrino measurements also raise questions. These particles travel directly from the core to detectors on Earth. Over the past few decades, the data have become more precise. They show that the actual fusion rate matches predictions for the total amount of energy produced, but they also suggest the reactions happen with less variation over time than the models allow. In other words, the Sunday does not have the small pulses of activity that scientists expected to see. Some researchers compare this to a well-regulated engine. In a car, sensors and valves keep fuel burning evenly, so the engine runs smoothly. The Sunday may have natural processes that work like those controls, but they are not fully understood. For instance, interactions between different fusion pathways could act like a safety net, preventing runaway changes in temperature. The mystery of the Sunday's steady burning matters beyond understanding our star. If scientists can explain why the Sunday is so efficient, it will improve models of other stars and help predict how they evolve. For now, the Sunday's perfect balance remains one of the most fascinating puzzles in astrophysics. When the Sunday fuses hydrogen into helium in its core, it releases vast amounts of energy. Most of this energy eventually reaches us as light and heat. Along with it, the reactions produce tiny particles called neutrinos. These particles have almost no mass and rarely interact with matter, so they travel straight from the core to Earth without being stopped. Because they come directly from the fusion zone, they give scientists a way to study the Sunday's inner workings. By counting neutrinos, researchers can test whether their models of solar fusion are correct. For many years, the numbers did not match. Early experiments, such as the one run deep inside a mine in South Dakota, consistently detected only about 1/3 of the neutrinos predicted by theory. This result was puzzling because it suggested either the models of the Sunday were wrong or something strange was happening to the neutrinos themselves. Scientists carefully checked the models, measuring the Sunday's brightness and composition in other ways, and everything else lined up. The problem seemed to lie with the neutrinos, but no one knew why. To understand this mystery, think of it like counting cars leaving a factory. If you expect 300 cars to leave every day, but only see 100 arrive at the parking lot, you might first suspect production has slowed. But if factory reports show production is steady, then maybe some of the cars are taking a different route, and you are not seeing them. This idea led to the concept of neutrino oscillation. According to this theory, neutrinos come in 3 types or flavors, and they can change from one type to another while traveling through space. Early detectors were designed to catch only one flavor, so they were missing the others. New experiments were built to test this. The Sudbury Neutrino Observatory in Canada used heavy water to detect all 3 flavors of neutrinos. When the data came in, they confirmed that the total number of neutrinos matched the predictions, solving much of the puzzle. The missing neutrinos had not vanished. They had simply changed form on their way from the Sunday to Earth. This discovery was a major breakthrough and showed that neutrinos have mass, which was a surprise to physicists. Even with this progress, some questions remain. Measurements still show small differences between expected and observed numbers, especially for certain energy ranges. These gaps suggest there may be more to learn about how neutrinos behave or how fusion works under extreme conditions. Some theories propose that subtle effects inside the Sunday's magnetic fields or interactions with dark matter could play a role. Modern detectors, buried deep underground to avoid interference, continue to collect data. They watch for rare signals as neutrinos pass through the Earth without stopping. Each detection adds a piece to the puzzle. The Sunday keeps sending out streams of these elusive particles, carrying secrets from its core that scientists are still working to decode. The Sunday's core is usually pictured as a smooth, perfectly balanced sphere, where hydrogen fuses into helium at the same rate everywhere. This simple image works well for many models, but new evidence hints that the reality may be more complex. There are signs that fusion reactions may not happen evenly across the entire core. Some regions could be slightly more active, while others produce less energy. Even a small difference spread over such a massive area could affect how energy moves through the Sunday. Fusion depends on temperature and density. The hotter and denser a region is, the more often hydrogen nuclei collide and fuse. If one part of the core is just a little hotter or denser than its surroundings, fusion there will occur more rapidly. The extra energy created could heat nearby material and push it outward, lowering its density, while cooler areas may be squeezed by gravity, becoming denser and hotter. This constant push and pull acts like a natural stabilizer, but it might not erase all unevenness. Some variations could persist for long periods. Scientists study these processes using helioseismology, which measures vibrations on the Sunday's surface caused by sound waves traveling through its interior. These waves move at different speeds depending on the density and structure of the material they pass through. By mapping these vibrations, researchers can infer what is happening deep inside, much like geologists use earthquake data to study Earth's layers. Some of these measurements hint at irregularities that may come from uneven fusion activity. Neutrinos, tiny particles released directly from fusion reactions, provide another clue. They travel straight from the core to detectors on Earth without being absorbed or scattered. If fusion were perfectly uniform, neutrino levels would remain steady and predictable. Instead, subtle fluctuations have been detected, suggesting that some regions of the core may be more active than others, even if the differences are small. To picture this, imagine a pot of thick soup heating on a stove. The heat does not spread evenly at first. Some parts bubble and boil while others stay cooler, especially before the soup is stirred. Over time, the motion of the liquid evens things out, but small hot spots still form and shift. The Sunday's core could behave in a similar way, though on a far greater scale and under extreme pressure. Magnetic fields and the Sunday's slow rotation may also play roles in shaping this unevenness. These forces can alter how plasma moves deep inside, creating complex patterns that affect fusion rates. While most of the time the Sunday's overall energy output stays steady, the hidden details of how fusion unfolds may be far more dynamic than the smooth models suggest. Understanding these variations could help explain subtle changes in solar behavior and improve our knowledge of how stars evolve. The Sunday's magnetic fields come from the motion of charged particles deep inside it. The Sunday is made of plasma, a state of matter where atoms are so hot that their electrons are stripped away. This plasma is filled with free-moving particles that carry electric charge. When these charged particles move, they create electric currents. These currents, in turn, produce magnetic fields. Because the Sunday is enormous and constantly in motion, there are countless flows of plasma generating and shaping these fields at the same time. Most of this activity happens in the convection zone, a layer beneath the Sunday's surface. In this zone, hot plasma rises while cooler plasma sinks, much like water boiling in a pot. As the plasma moves in these looping patterns, it drags magnetic field lines with it, stretching and twisting them. This process builds up strength in the fields and creates complex shapes. The Sunday also rotates, but it does not spin as a solid object. The equator rotates faster than the poles, a phenomenon known as differential rotation. Over time, this difference stretches the magnetic field lines even more, wrapping them around the Sunday like threads wound on a spool. The combined effects of convection and differential rotation form what scientists call a dynamo. A dynamo is a system that turns motion into magnetic energy. On Earth, the core of molten iron acts as a dynamo that generates the planet's magnetic field. The Sunday's dynamo works in a similar way, but on a far larger and more turbulent scale. Because plasma flows are constantly shifting, the solar magnetic field is never static. It grows stronger, twists, and sometimes reconnects, releasing bursts of energy that we see as solar flares or eruptions of plasma called coronal mass ejections. The Sunday's magnetic field also follows a repeating cycle that lasts about 11 years. At the start of a cycle, the field is relatively simple, with a clear north and south pole. As time passes, the field becomes more tangled, and sunspots begin to appear where the twisted fields push through the surface. These sunspots usually come in pairs with opposite magnetic polarity. As the cycle continues, the fields grow more complex until they eventually break apart and reorganize. When this happens, the Sunday's magnetic poles flip, with north becoming south and south becoming north, and a new cycle begins. The exact details of how the solar dynamo works remain uncertain. The boundary between the stable inner layers and the turbulent convection zone, called the tachocline, may play a key role. Shear forces in this region could help amplify magnetic fields before they rise to the surface. While many parts of the process are still hidden, ongoing observations and computer models continue to reveal how the Sunday's constant motion creates the powerful magnetic fields that shape its activity and affect the entire solar system. Sunspots are dark patches that appear on the surface of the Sunday. They seem dark because they are cooler than the areas around them, though they are still thousands of degrees hotter than anything on Earth. A sunspot forms when intense magnetic fields rise up from beneath the surface and block the normal upward flow of heat. This trapped heat lowers the temperature in that region, creating a dark spot against the Sunday's brighter background. Sunspots are signs of magnetic activity, and they follow repeating patterns that reveal what is happening deep inside the Sunday. The Sunday's magnetic fields are generated by the motion of plasma inside it. Plasma is a hot, electrically charged gas in the Sunday's outer layers called the convection zone. Hot plasma rises, cools, and sinks again, like water boiling in a pot. These motions move charged particles, creating electric currents. The Sunday also rotates, but its equator spins faster than its poles. This uneven motion, known as differential rotation, stretches and twists the magnetic field lines over time. The combination of convection and rotation forms a magnetic dynamo that constantly builds and reshapes the Sunday's fields. As the magnetic fields become more twisted and stressed, they can no longer stay below the surface. When the tension grows too strong, parts of the field push upward, breaking through the surface in looping shapes. At the points where the magnetic field emerges, sunspots appear in pairs. One spot marks where the field comes out, and the other marks where it dives back down. These spots have opposite magnetic polarity, like the north and south ends of a magnet. Bright arcs of plasma often connect them, showing the shape of the field lines above the surface. Sunspots do not appear randomly. At the start of a solar cycle, they form in two bands on either side of the Sunday's equator, roughly halfway between the equator and the poles. As the cycle continues, new spots appear closer to the equator. When scientists plot the locations of sunspots over time, the pattern looks like the wings of a butterfly, which is why it is called a butterfly diagram. This movement reflects changes in the Sunday's internal magnetic structure as the cycle progresses. The number of sunspots also rises and falls in a regular pattern lasting about 11 years. At first, only a few spots appear. Then the number increases until it reaches a peak, called solar maximum. During this time, the Sunday is highly active, with frequent flares and eruptions. After the peak, the magnetic fields begin to break apart and reorganize, and the number of sunspots drops to a minimum. At this point, the Sunday's magnetic poles flip, and a new cycle begins. These repeating cycles show how deeply connected the Sunday's surface activity is to the invisible motions and magnetic forces hidden beneath it. Deep inside the Sunday, waves move through layers of hot plasma, carrying information about the conditions hidden far below the surface. These waves cannot be seen directly, but they make the surface of the Sunday shift in tiny rhythmic ways. By carefully measuring these surface movements, scientists can trace the waves back to their source. This method, called helioseismology, works like using sound waves to explore the inside of Earth. Geologists study how earthquake vibrations move through rock, and in the same way, solar scientists study these solar vibrations to map the Sunday's interior. Standard models of the Sunday predict how these waves should travel. The speed and path of the waves depend on the temperature, density, and composition of the material they move through. If the models are correct, the patterns of waves at the surface should match the predictions. But observations reveal differences that point to something unexpected. Some waves travel slightly faster or slower than the models suggest, while others curve or twist in ways that should not happen in a perfectly smooth layered interior. These strange results hint that the Sunday's inner structure may be more complicated than once believed. To understand this, imagine striking a perfect bell. A flawless bell rings with a clear, steady tone. If the bell has cracks or uneven spots, the sound becomes distorted. The Sunday acts like that bell. The vibrations it produces carry traces of flaws or irregularities deep inside. The differences between expected and observed wave patterns are like hearing a distorted note and knowing something inside the bell is off. One explanation could be that the boundary between the stable inner region and the turbulent outer layer, called the tachocline, is more complex than expected. This layer might have swirling currents or sudden changes in density that scatter the waves. Another possibility is that strong magnetic fields deep below the surface are bending the waves. These hidden magnetic fields are difficult to measure directly, but their presence could explain why the waves behave differently than predicted. Some wave patterns also change slowly over time. These shifts seem to match the rise and fall of solar activity during the 11-year solar cycle. This link suggests that the same processes that create sunspots and flares may also be shaping the flow of plasma deep inside the Sunday. A helpful way to picture this is to think of ripples on a lake. On a calm day, the ripples move in neat, predictable circles. On a windy day with unseen currents beneath the surface, the ripples scatter and twist unpredictably. The strange helioseismic signals are like those twisted ripples. They reveal that the Sunday's deep interior is not calm and uniform, but dynamic and full of hidden motion. Each measurement offers a clue, helping scientists uncover the complex processes driving the heart of our star. The Sunday's core has remained remarkably stable for billions of years, allowing it to produce a steady flow of energy that reaches Earth as sunlight. Other stars of similar size often show more variation, with sudden changes in brightness or bursts of activity. This stability comes from a delicate balance between two opposing forces. Gravity pulls the Sunday's mass inward, trying to make it collapse, while the energy released by nuclear fusion pushes outward. When these forces are in perfect balance, the Sunday remains stable, neither shrinking nor expanding too quickly. In the core, hydrogen atoms fuse into helium under extreme heat and pressure. This process releases energy in the form of light and particles. If the core gets slightly hotter, fusion speeds up, releasing more energy. The extra energy causes the core to expand a little, which lowers the temperature and slows fusion back down. If the core cools, gravity causes it to contract, which raises the temperature and speeds up fusion again. This self-correcting system acts like a natural thermostat, keeping the core temperature and pressure steady over time. Many stars of similar size have less even behavior because their interiors are more turbulent, or their fusion reactions are less balanced. In some stars, the outer layers are unstable and create pulses of energy that travel inward and disturb the core. In others, changes in composition make fusion run too fast or too slow, leading to cycles of swelling and shrinking. The Sunday's internal structure is unusually calm. Its convection zone, where hot plasma rises and cooler plasma sinks, is deep and efficient at moving energy outward. This prevents heat from building up unevenly and keeps the fusion rate smooth. Another factor is the Sunday's rotation. It spins at a moderate speed, not too fast and not too slow. Faster rotation in similar stars can create stronger magnetic fields and violent mixing inside the star, which can lead to instability. The Sunday's slower rotation limits this effect, keeping its magnetic activity mostly confined to the outer layers rather than disrupting the core. 2. Picture this balance. Imagine a campfire. If you pile on too much wood at once, the fire flares wildly and burns unevenly. If you let it die down too much, it struggles to keep burning. The Sunday is like a fire that constantly adjusts itself, adding just enough fuel at the right pace to keep a steady flame. This stability has allowed the Sunday to shine with nearly the same output for billions of years. That steady energy has given Earth a consistent environment where life could develop and grow. While other stars may flicker or flare unpredictably, the Sunday's core works like a finely tuned engine, always adjusting to keep itself in balance and producing the light and heat that sustain our planet. About 4.6 billion years ago, the Sunday began forming from a vast cloud of gas and dust in space. This cloud, known as a molecular cloud, contained hydrogen, helium, and traces of heavier elements left behind by earlier generations of stars. Something disturbed this cloud, perhaps a nearby supernova or a passing shockwave. The disturbance caused parts of the cloud to clump together. As these clumps grew denser, gravity pulled in more material, starting a slow collapse that marked the first stage of the Sunday's birth. As the material fell inward, it formed a spinning disk. Most of the mass gathered at the center, creating a growing ball of gas called a protostar. The rest of the disk spread out around it, where planets, moons, and smaller bodies would later form. The spinning motion helped keep the material from collapsing too quickly, while gravity continued to pull everything toward the center. Over time, the pressure and temperature inside the forming protostar, when the core reached about 10 million degrees Celsius, nuclear fusion began, turning hydrogen into helium and releasing energy. This moment marked the true birth of the Sunday as a star. While this basic outline is widely accepted, the exact timeline of these events remains debated. Some scientists think the process took only a few million years from the first collapse to the start of fusion, while others believe it happened more slowly. The challenge comes from the lack of direct evidence. We cannot go back and watch the Sunday form, so researchers study other young stars and remnants of ancient material in meteorites to piece together the story. These clues show that the early solar system was a violent place, with collisions, intense radiation, and powerful stellar winds shaping its development. One mystery involves how quickly the Sunday cleared away the surrounding gas and dust after fusion began. The young Sunday would have given off strong bursts of radiation and streams of charged particles. These forces could have blown away much of the remaining material, but the timing is uncertain. If this happened too soon, there might not have been enough material left to form planets like Earth. If it happened too late, the inner planets might have grown too large or been pulled into the Sunday. Another question centers on the role of nearby stars. The solar system likely formed in a cluster, with many other stars born around the same time. Their gravity and radiation could have influenced the early stages of the Sunday's growth. For example, a close encounter with another star might have shaped the outer regions of the solar system or affected the path of comets and asteroids. By studying young star forming regions in our galaxy, scientists continue to refine their models of how the Sunday came to be. Each new observation adds to our understanding, but the exact sequence and timing of the events that led to the Sunday's birth remain pieces of a puzzle that is still being solved. The Sunday's surface, called the photosphere, has a temperature of about 5,500 degrees Celsius. Above it lies the corona, the Sunday's outer atmosphere, which stretches millions of kilometers into space. Strangely, the corona is far hotter than the surface. reaching temperatures of several million degrees. This is the opposite of what most people would expect. Normally, heat decreases with distance from its source, like the way air cools as you move away from a fire. This mystery is known as the corona heating problem, and it has puzzled scientists for decades. Energy must be flowing from the lower layers of the sundae into the corona, but the exact process is not fully understood. One idea involves magnetic fields. The sundae's surface is covered with constantly shifting magnetic loops that rise and fall as the plasma beneath moves. These loops can twist and snap, releasing bursts of energy. When this happens, it could send heat into the corona. The process is similar to stretching a rubber band until it breaks and releases stored energy, but on a much larger scale and with magnetic forces instead of tension. Another possible explanation comes from waves moving through the plasma. The sundae's surface constantly shakes and vibrates because of the motions inside it. These vibrations may create special kinds of waves called alpha-Fen waves that travel along magnetic field lines. If these waves reach the corona, they could dump their energy there, heating the plasma. The challenge is that while these waves have been detected, it is difficult to measure whether they carry enough energy to explain the extreme temperatures. To picture this, imagine a pot of water on a stove. The bottom of the pot is the photosphere, and the space above it is the corona. Normally, the water near the bottom would be the hottest, but if someone stirred the pot with great force or dropped sparks into it, you might find the top layer heating up more than expected. In the sundae's case, the stirring comes from magnetic fields and plasma motion, while the sparks are bursts of energy released during magnetic events. Spacecraft such as NASA's Parker Solar Probe and the European Space Agency's Solar Orbiter are now flying closer to the sundae than ever before to study this problem. They measure magnetic fields, plasma flows, and particles in the corona to look for signs of how the heating occurs. Early data suggest that both magnetic reconnection and wave heating may play roles, with different processes dominating in different regions. The corona heating problem remains one of the most important unanswered questions in solar physics. Solving it will not only reveal how the sundae works, but also improve our understanding of space weather, which affects satellites, power grids, and communication systems on Earth. Coronal holes are large, dark regions that appear in the sundae's outer atmosphere, or corona, when viewed in ultraviolet light. They look darker because they are cooler and less dense than the surrounding areas. These regions are important because they are the main sources of high-speed solar wind streams, which are flows of charged particles that travel outward through the solar system. When these streams reach Earth, they can disturb our planet's magnetic field and create auroras, as well as disrupt satellites and communication systems. While coronal holes are a well-known feature, the exact reasons why they form and how they accelerate the solar wind are still not fully understood. Coronal holes are linked to the sundae's magnetic field. Normally, magnetic field lines loop back into the sundae's surface, trapping plasma and holding it in place. In a coronal hole, the field lines stretch outward into space, instead of looping back. This open configuration allows particles to escape freely, creating a steady outflow of solar wind. Scientists believe that differences in the sundae's magnetic activity control where these open field lines form. However, predicting when and where coronal holes will appear remains difficult, because the sundae's magnetic field is constantly shifting as plasma moves beneath the surface. The solar wind that escapes from coronal holes travels much faster than the slower solar wind from other regions. In these areas, particles can reach speeds of over 800 kilometers per second. What causes this rapid acceleration is still debated. One idea is that waves traveling along magnetic field lines, known as alpha-Fen waves, transfer energy to the particles, pushing them outward. Another theory suggests that small, frequent magnetic reconnection events, where magnetic field lines break and reconnect, release bursts of energy that fling particles into space. It is possible that both processes are involved, with different mechanisms playing larger roles in different parts of the corona. Coronal holes also follow patterns related to the Sunday's 11-year activity cycle. During periods of high activity, when sunspots and flares are common, coronal holes are smaller and more scattered. During quieter periods, especially near solar minimum, coronal holes can grow much larger and last for many months. When a large coronal hole rotates to face Earth, it often sends a stream of high-speed solar wind directly toward our planet. This can trigger geomagnetic storms that affect power grids and navigation systems. To imagine how coronal holes work, think of the Sunday's magnetic field as a tangled forest of ropes. In most places, the ropes are tied together in loops, holding material close. In a coronal hole, some ropes are cut and stretch outward, letting material escape freely. Spacecraft such as NASA's Parker Solar Probe are now collecting data close to the Sunday to better understand these regions. By studying the structure of the magnetic fields and the flow of particles, scientists hope to explain why coronal holes form and how they drive the fastest streams of the solar wind. Solar flares are sudden bursts of energy released from the Sunday's surface. They produce intense light, heat, and streams of charged particles that travel through space. When aimed at Earth, they can disrupt satellites, power grids, and communication systems. While scientists understand that flares are linked to the Sunday's magnetic activity, the exact trigger that sets off these massive events remains uncertain. The Sunday's surface is shaped by constantly moving plasma. This plasma carries electric charges, which create magnetic fields. These fields twist and tangle as the plasma churns beneath the surface, and as the Sunday rotates. Over time, the magnetic lines become stressed, storing large amounts of energy. Most of the time, this energy remains trapped below the surface, like tension in a tightly coiled spring. At some point, the stress builds until something causes the field lines to snap and reconnect, in a process called magnetic reconnection. This sudden release of magnetic energy produces a solar flare. The mystery lies in what exactly pushes the system past its breaking point. In some cases, a slow buildup of stress may be enough to cause a sudden failure, much like a bridge collapsing after years of strain. In other cases, a smaller local event may act as the spark. For example, a nearby eruption or shifting plasma flow could destabilize a larger magnetic structure, leading to a chain reaction. This is similar to how a small rock slide can trigger a much larger avalanche on a mountain slope. Sunspots play a key role in flare formation. These dark regions mark areas where magnetic fields are especially strong and concentrated. Flares often occur near clusters of sunspots, where magnetic lines of opposite polarity are close together. When these opposing fields interact, they can create unstable conditions. If the magnetic lines cross and reconnect, huge amounts of energy are released in seconds. The size of a flare depends on how much magnetic energy was stored beforehand. Smaller flares release limited bursts of radiation, while the largest flares unleash energy equivalent to billions of nuclear bombs exploding at once. These powerful flares can also trigger coronal mass ejections, where vast clouds of plasma are hurled into space. Scientists use spacecraft and solar observatories to watch these events in real time. Instruments capture changes in magnetic fields and plasma flows leading up to a flare. By comparing data from many events, researchers hope to identify common patterns that reveal the final trigger. Some studies suggest that twisting motions deep in the Sunday's convection zone may slowly load energy into the surface layers until a sudden shift releases it. Despite these efforts, predicting solar flares remains difficult. The Sunday's surface is vast and complex, with countless magnetic interactions happening at once. Each flare is a reminder that even small changes in these tangled fields can unleash tremendous power when the right conditions align. The Sunday usually follows clear and predictable patterns of activity. Its brightness changes slowly over time, rising and falling with the 11-year solar cycle. During solar maximum, the surface shows many sunspots, flares, and eruptions, while during solar minimum, it is quieter and more stable. However, there are times when the Sunday suddenly brightens in ways that do not fit this cycle. These rapid changes happen without warning and are not fully explained by current models of solar behavior. These sudden brightenings can occur across different parts of the Sunday's atmosphere. Some appear in the lower layers, near the surface, while others happen higher up in the corona. They are often very brief, lasting only minutes or hours, but the amount of energy released can be enormous. Unlike solar flares, which are usually tied to strong magnetic activity around sunspots, these brightenings sometimes occur in regions where no obvious magnetic structures are present. This makes them harder to study and predict. One impossible explanation involves small-scale magnetic reconnection events. Magnetic fields on the Sunday are constantly shifting as plasma moves beneath the surface. Even in areas that look quiet, there may be complex, tangled fields below. If these fields suddenly snap and reconnect, they could release bursts of energy, creating a short-lived brightening. This would be similar to a hidden fault line on Earth, triggering a sudden earthquake. The problem is that these events are so small and fast that detecting them directly is extremely difficult. Another theory suggests that waves moving through the Sunday's plasma may play a role. The Sunday vibrates constantly because of motions deep inside. Some of these vibrations travel upward as waves that carry energy into the outer layers. If these waves interact in just the right way, they could focus their energy and cause a rapid, localized burst of heat and light. This is like ocean waves combining to create a single, unexpectedly large wave, even on a calm sea space. Based observatories have captured images of these brightenings, showing that they can occur almost anywhere on the surface. Some appear as small, intense points of light, while others spread across larger areas. They do not always match the timing of solar flares or other well-known events. This suggests that they may be driven by processes separate from the main solar cycle. Studying these brightenings is challenging because they happen so quickly. Instruments must capture data at very high speeds and in multiple wavelengths of light to reveal what is really occurring. Missions like NASA's Solar Dynamics Observatory and the Parker Solar Probe are providing more detailed views than ever before, but the cause remains uncertain. Each observation adds a piece to the puzzle, helping scientists understand how even quiet regions of the Sunday can produce sudden, powerful bursts of energy that defy current models of solar behavior. Magnetic reconnection is a process where magnetic field lines in plasma break apart and then join together in a new arrangement. This process releases a large amount of energy in a very short time. On the Sunday, magnetic reconnection drives some of its most powerful events, such as solar flares and coronal mass ejections. These events can send huge amounts of charged particles into space and affect satellites and power systems on Earth. Even though scientists know reconnection happens, the exact physics behind how it works remain unclear. The Sunday's plasma is filled with moving electric charges that create magnetic fields. These fields are not fixed. They are constantly stretched and twisted by the motion of the plasma. In many areas, the magnetic lines form closed loops that connect back to the surface. As the loops shift and interact, they can become tangled and stressed. When two sets of magnetic lines with opposite direction come close together, they can break and reconnect. This sudden change in configuration releases energy, heating the surrounding plasma and accelerating particles outward. To picture this, imagine two ropes stretched tight and twisted together. As the tension builds, a section might snap and reattach in a different way, releasing stored energy. In the Sunday, The ropes are invisible magnetic fields, and the snapping happens across enormous distances. The problem is that magnetic fields themselves cannot break in a vacuum, so the actual breaking must happen through the plasma. The particles in the plasma somehow allow the field lines to change their connections, but the details of how this occurs are still being studied. Lone mystery involves the speed of reconnection. In many solar events, the process happens far faster than current theories predict. According to basic physics, it should take much longer for magnetic lines to rearrange. This suggests that there are small-scale effects at work that scientists do not yet fully understand. Turbulence, tiny electric currents, or special kinds of waves may help the fields snap and reconnect more quickly, but evidence is incomplete. Spacecraft such as NASA's magnetospheric multiscale mission have observed reconnection in Earth's magnetic field, providing valuable clues. These measurements show that even very small regions of plasma can play a key role. The Sunday's environment is far more extreme, with higher temperatures and stronger magnetic forces, making direct observations much harder. Computer simulations are used to test ideas, but they must simplify the physics to be practical. As a result, they can capture the broad behavior of reconnection, but miss some of the fine details. Understanding this process is vital because it explains how magnetic energy builds up and then explodes outward. Each step towards solving this puzzle brings scientists closer to predicting when the Sunday might unleash a powerful flare or storm, giving us more time to protect our technology and systems here on Earth. The Sunday's surface is constantly shifting and changing, with plasma rising, falling, and flowing in complex patterns. Among the most striking features are mysterious plasma jets, narrow streams of hot material that shoot upward from the surface at very high speeds. These jets move at hundreds of kilometers per second and reach far into the Sunday's outer atmosphere, or corona, before fading away. They are small compared to giant solar flares or eruptions, but they are incredibly common. Thousands of them may be active across the Sunday at any given moment, making them a key part of the Sunday's dynamic behavior. Plasma jets are puzzling because their exact cause is not fully understood. They appear suddenly and last only a few minutes, which makes them difficult to study in detail. Most of them form near areas with strong magnetic activity, such as the edges of sunspots or regions where magnetic fields are tangled. This suggests that magnetic forces play a major role in launching them. One leading idea is that magnetic reconnection is involved. As the Sunday's plasma moves, it drags magnetic field lines with it. When two sets of field lines cross and reconnect, they release a burst of energy. This energy could push plasma upward in a narrow, fast-moving jet. It is similar to how a snapped rubber band releases tension, except on a far larger scale and with magnetic fields instead of rubber. Another theory focuses on waves moving through the Sunday's atmosphere. The surface is constantly vibrating due to motions deep inside. Some of these vibrations may form special waves that travel along magnetic field lines. If these waves carry enough energy, they could push plasma upward, forming a jet. It is possible that both mechanisms are at work, with magnetic reconnection providing a sudden burst and waves supplying a steady push. Observations show that there are different types of jets. Some are small and quick, disappearing within a minute, while others are larger and last longer. The smaller ones, called spicules, are so numerous that they may play an important role in heating the corona and driving the solar wind. Larger jets can sometimes merge or trigger other events, linking them to bigger solar phenomena like flares or eruptions. Studying these jets requires high-speed, high-resolution instruments. Spacecraft such as NASA's Solar Dynamics Observatory and the Parker Solar Probe have captured images and measurements of jets in action. These observations reveal fine details of their shape, speed, and temperature, offering clues about their origin. To imagine how plasma jets behave, think of boiling water in a pot. Bubbles rise and burst constantly, sending tiny sprays upward. The Sunday's surface acts like that pot, but instead of water, it is plasma driven by intense magnetic and thermal forces. Understanding how these jets form and how they transfer energy may help explain some of the Sunday's most persistent mysteries, including why its outer atmosphere is so hot and how the solar wind begins. The Sunday's surface is never still. It constantly shifts and moves as energy from deep within pushes upward. Among these motions are strange rhythmic waves known as surface oscillations. These are not small ripples, but massive patterns that stretch across vast regions of the Sunday. They rise and fall in repeating rhythms, like the slow breathing of a living thing. Scientists first detected them by noticing subtle changes in the light coming from the Sunday, which suggested that parts of the surface were moving toward and away from us in regular cycles. These oscillations are created by sound waves trapped inside the Sunday. Deep below the surface, turbulent motions from the convection zone send vibrations upward. Instead of escaping into space, these waves bounce back and forth inside the Sunday, trapped by differences in density and temperature between the layers. The surface then acts like the skin of a drum, responding to the vibrations beneath. By studying how the surface moves, scientists can learn about the conditions deep inside, just as seismologists use earthquake waves to study Earth's interior. In theory, the patterns of these waves should match predictions based on models of the Sunday's structure. Many of them do, which has helped confirm key parts of our understanding, such as the depth of the convection zone and the speed of internal flows. But some waves do not behave as expected. Certain oscillations travel faster or slower than models predict. Others shift over time in ways that cannot be explained by the known solar cycle. These differences suggest that something about the Sunday's interior is more complex than current theories allow. One possible cause is hidden magnetic fields beneath the surface. Magnetic forces are known to shape the Sunday's outer activity, creating sunspots and flares. If there are strong magnetic fields buried deep below, they could change the way the waves move, bending or speeding them up. Another possibility is that the layers of plasma are not as smooth as once thought. If there are irregular flows or differences in composition, they could scatter the waves and create unusual patterns. To picture how this works, imagine tapping a perfect drum. A flawless drumhead produces a clear, predictable tone. If the drumhead has weak spots or uneven tension, the sound becomes distorted. Drumhead. Its strange oscillations are the distorted notes, revealing hidden structures or movements beneath. These oscillations also change slowly over time. Some appear to rise and fall in sync with the 11-year solar cycle, while others shift independently. This suggests that multiple processes are influencing the waves at once. Space-based observatories, like the Solar Dynamics Observatory, track these oscillations in great detail, capturing minute movements across the entire Sunday. Each new set of data adds clues about the deep unseen forces shaping the Sunday's behavior and helps scientists refine their models of how our star works. The Sunday's surface, when viewed through powerful telescopes, shows a pattern that looks like a field of tiny shifting cells. These cells are called granules. Each granule is a region of hot plasma rising from below the surface. As the plasma reaches the top, it spreads outward, cools, and then sinks back down around the edges. This constant motion creates a grainy texture, similar to bubbles in a pot of boiling water. Granules are enormous by earthly standards, typically around 1,000 kilometers across. Yet, they are only a small part of the Sunday's surface activity. The basic process behind granulation is well understood. The outer layer of the Sunday, known as the convection zone, moves heat upward through churning motions. Hotter plasma rises because it is lighter, while cooler plasma sinks because it is heavier. This cycle repeats endlessly, carrying energy from the Sunday's interior to its surface. The visible tops of these convection currents are the bright centers of granules, while the darker edges mark where cooler plasma is sinking. From a distance, these bright and dark areas blend together, creating the Sunday's shimmering appearance. While the overall behavior of granules is clear, the fine details remain partly unexplained. High-resolution images show that the edges of granules are far more complex than simple convection patterns would predict. The borders twist and change shape rapidly, forming intricate, turbulent structures. Some granules merge together, while others break apart suddenly. These changes happen on timescales of minutes, suggesting that small-scale forces are influencing their behavior. One puzzle is the role of magnetic fields. The Sunday's surface is threaded with countless magnetic field lines that rise and fall with the motion of plasma. In some areas, these fields seem to shape the flow, guiding where plasma can rise or sink. In other regions, the plasma appears to move freely, as if the magnetic fields are too weak to have much effect. Understanding how these forces interact on such small scales is difficult. It may be that magnetic effects only become important when plasma flows reach certain speeds or densities, creating sudden changes in granule patterns. Another mystery involves how energy moves between different layers of the Sunday. The transition from the visible surface to the outer atmosphere, or corona, is still not fully understood. Granules may play a role in transferring energy upward, possibly through waves or small bursts of motion. These effects are hard to measure directly because they occur in narrow, fast, moving regions that require extremely precise instruments to study. To visualize granules, imagine watching boiling water up close. The bubbles rise and burst constantly, creating patterns that shift from second to second. The Sunday's surface works the same way, but on a scale so vast that each bubble is larger than an entire continent. The fine details of these patterns hold clues about how heat, motion, and magnetic fields interact in the outermost layers of our star, revealing processes that are still only partly understood. The Sunday's magnetic poles are not fixed, like Earth's about every 11 years. They switch places. The North Pole becomes the South Pole, and the South Pole becomes the North. This flip is part of the solar cycle, which is closely linked to the rise and fall of sunspots on the Sunday's surface. Sunspots are areas where magnetic fields are especially strong and block heat from rising, making those regions appear darker as the number of sunspots increases and decreases over the cycle. The magnetic field slowly reorganizes itself until it finally reverses. The process begins deep within the Sunday, in a region called the convection zone. Here, hot plasma rises and cooler plasma sinks, carrying charged particles with it. Moving charges create electric currents, which in turn generate magnetic fields. The Sunday also rotates, but it does not spin evenly. The equator rotates faster than the poles, a motion called differential rotation. This difference stretches and twists the magnetic field lines over time. At first, the Sunday's magnetic field is simple and aligned with its poles, like a bar magnet. As differential rotation winds the field lines, they become tangled and looped. These twisted fields push through the surface, forming sunspots in pairs. One sunspot marks where the magnetic field rises from the surface, and the other marks where it dives back down. The two spots have opposite magnetic polarity. Early in the cycle, sunspots appear at mid-latitudes, roughly halfway between the equator and poles. As the cycle progresses, new sunspots emerge closer to the equator. This pattern, when tracked over time, forms what scientists call a butterfly diagram, because the spots trace a shape like butterfly wings. As more sunspots appear and magnetic fields grow stronger, they begin to interfere with one another. Gradually, the original large-scale magnetic field weakens. Near the peak of the cycle, called solar maximum, the Sunday's surface is covered with complex, tangled magnetic structures. During this time, magnetic loops break and reconnect in a process known as magnetic reconnection, releasing energy in the form of solar flares and eruptions. These events help rearrange the Sunday's magnetic field into a new configuration. Eventually, the tangled fields reorganize so completely that the Sunday's overall magnetic polarity flips. After the reversal, the field settles into a simpler state again, but now the poles are swapped. The cycle then repeats, with a new set of sunspots appearing, and the process starting over. The entire sequence takes about 11 years, though the exact timing can vary. So picture this. Imagine twisting a long rope. At first, the rope is straight, like the Sunday's simple magnetic field at the start of a cycle. As you keep twisting, knots and loops form, like sunspots. If you twist enough, the entire rope flips over, just as the Sunday's magnetic field reverses. This constant flipping drives the rhythm of solar activity and shapes many of the phenomena we see on the Sunday's surface and in space around it. The Sunday constantly releases energy across many wavelengths of light, including ultraviolet or UV radiation. Most of this UV emission follows predictable patterns tied to the solar cycle and the Sunday's surface activity. When sunspots, flares, and other magnetic events increase, UV levels rise in a steady way. However, scientists have observed sudden spikes of ultraviolet radiation that do not fit these expected patterns. These bursts happen without warning, sometimes in regions of the Sunday that appear quiet, and their cause remains uncertain. UV radiation comes mainly from the Sunday's outer layers, especially the chromosphere and the corona. These layers are made of superheated plasma, shaped by powerful magnetic fields. Normally, UV levels increase during large, visible events, like solar flares. In those cases, the source of the radiation is clear. The puzzling emissions are different. They appear quickly, rise sharply, and fade just as fast, often without any visible changes on the surface. Instruments detect them as brief flashes of energy, sometimes lasting only minutes, making them difficult to study in detail. One possibility is that these emissions are caused by very small magnetic reconnection events. Magnetic fields beneath the surface are constantly shifting as plasma moves. Even in regions that look calm, there may be tangled fields storing energy. If two sets of magnetic lines cross and reconnect on a small scale, they could release sudden bursts of energy too small to create a visible flare, but strong enough to produce a spike in UV radiation. This would be like a tiny spark in an electrical circuit, invisible to the eye, but still powerful. Another theory involves waves moving through the Sunday's plasma. The surface and lower layers are filled with constant vibrations caused by motions deep inside. Some of these vibrations form special waves that travel upward along magnetic field lines. If these waves interact in just the right way, they might focus energy into narrow areas, briefly heating the plasma and releasing UV radiation. This process would be similar to ocean waves combining to form a single, unexpectedly large wave that appears and disappears quickly. These sudden UV spikes are not just a scientific curiosity. Ultraviolet radiation plays a major role in shaping Earth's upper atmosphere. A sharp increase in UV levels, even for a short time, can affect satellite operations, radio communications, and GPS systems. Because the spikes are unpredictable, they add an element of risk to space weather forecasting. Spacecraft such as NASA's Solar Dynamics Observatory and the Parker Solar Probe monitor the Sunday continuously, capturing high-speed data across many wavelengths. These instruments have confirmed that the UV spikes are real and not errors in measurement. Each new observation adds pieces to the puzzle, showing when and where the spikes occur. By comparing these events to other solar activity, scientists hope to discover what hidden processes deep within the Sunday are releasing these sudden bursts of ultraviolet light and why they defy current models of solar behavior. The solar wind is a continuous stream of charged particles flowing out from the Sunday into space. It moves at incredible speeds, sometimes reaching over 800 kilometers per second. These particles, mostly electrons and protons, travel across the solar system and interact with planets, moons, and magnetic fields. On Earth, the solar wind helps create auroras and can disturb satellites, power grids, and communication systems. Scientists understand why the solar wind exists, but are still trying to explain how it accelerates to such extreme speeds. The solar wind begins in the corona, the Sunday's outer atmosphere. The corona is millions of degrees hotter than the Sunday's surface, which has a temperature of about 5,500 degrees Celsius. At such high temperatures, particles have enough energy to escape the Sunday's gravity, much like steam escaping from boiling water. This explains why there is a solar wind at all, but not why it travels so fast. If temperature alone drove the flow, the particles would move outward much more slowly than what we actually observe. One leading idea involves magnetic fields. The Sunday's surface is covered with constantly shifting magnetic loops. In some regions, these magnetic field lines do not loop back into the Sunday, but instead stretch far out into space. Plasma can flow freely along these open field lines, forming fast streams of solar wind. Waves known as alpha-Fen waves may travel along these lines, carrying energy outward. As the waves move, they could transfer energy to the particles, pushing them faster and faster. This is similar to how wind pushes a sailboat across water, adding speed over time. Another possibility is that small bursts of energy from magnetic reconnection play a role. In this process, magnetic field lines break and reconnect, releasing sudden bursts of heat and motion. Countless tiny reconnection events may happen across the Sunday's surface, like constant miniature explosions. Each event could give a slight boost to the particles, and together these bursts might provide enough extra energy to account for the solar wind's extreme speeds. Coronal holes, dark regions in the corona, are often linked to the fastest solar wind streams. In these areas, the magnetic field lines are wide open, allowing particles to escape more easily. Spacecraft observations show that when a large coronal hole rotates to face Earth, the solar wind becomes faster and more intense. This connection suggests that magnetic structure plays a critical role in both starting and accelerating the flow. The Parker Solar Probe is now traveling closer to the Sunday than any spacecraft before it. Its instruments measure magnetic fields, plasma flows, and particles at their source. Early data suggest that both waves and reconnection are involved, with different processes dominating in different regions. By combining these observations, scientists are slowly uncovering how the solar wind gains its speed and why it behaves differently in various parts of the Sunday's atmosphere. The heliosphere is a vast bubble of charged particles and magnetic fields, created by the solar wind. It surrounds the entire solar system and acts as a shield, protecting the planets from much of the radiation and high-energy particles coming from interstellar space. For a long time, scientists assumed the heliosphere was shaped like a comet, with a rounded front where the solar wind pushes outward and a long tail streaming behind as the solar system moves through the galaxy. However, data from spacecraft such as Voyager 1 and Voyager 2 show that the boundary is far more irregular than expected. The edge of the heliosphere, called the heliopause, marks the point where the solar wind slows down and mixes with particles from interstellar space. The shape of this boundary depends on the balance between the outward flow of the solar wind and the pressure of material from the space between stars. If this balance were even in all directions, the heliosphere would form a smooth, symmetrical bubble. Instead, measurements show that the boundary is uneven, with bulges and distortions. In some directions, the edge is much closer to the Sunday than in others. One reason for this irregular shape may be the magnetic field that fills interstellar space. As the solar system travels through the galaxy, it encounters this external magnetic field, which can push against the heliosphere unevenly. Imagine holding a balloon underwater while currents flow around it. The side facing a strong current will be pushed inward, while other areas may stretch outward. In a similar way, the external magnetic field and interstellar particles can distort the solar bubble. The solar wind itself also varies in strength and speed. During periods of high solar activity, such as solar maximum, the Sunday sends out faster, more powerful streams of particles. During quieter times, the flow is weaker. These changes ripple outward and can cause the boundary of the heliosphere to expand and contract over time. Because the solar wind is not uniform in all directions, some regions push outward more strongly, adding to the uneven shape. Recent data suggests the heliosphere might not have a single smooth tail at all. Instead, it could have two separate streams or even a blunt, rounded shape at the back. This was a surprise, as earlier models relied on the simpler comet. Like structure, the irregularities could come from complex interactions between solar particles and interstellar particles at the edge of the bubble. To picture this, think of a weather front on Earth. Winds and temperatures mix in messy, shifting ways, creating a boundary that is never perfectly straight. The heliopause behaves in a similar way, shaped by forces we cannot directly see. By studying particles and magnetic fields measured by the Voyager spacecraft and other missions, scientists are piecing together a clearer view of this invisible boundary and learning how the solar system interacts with the galaxy around it. Cosmic rays are high, energy particles that come from outside our solar system. They travel through space at nearly the speed of light and strike Earth's atmosphere constantly. Most cosmic rays come from distant sources like exploding stars, called supernovae, or other energetic events in the galaxy. As they move toward the solar system, they pass through the bubble of charged particles and magnetic fields created by the Sunday, known as the heliosphere. The activity of the Sunday strongly affects how many of these cosmic rays reach Earth and how they are distributed. The solar wind, a stream of particles flowing outward from the Sunday, acts as a barrier against incoming cosmic rays. When solar activity is high, the solar wind is faster and more turbulent. It strengthens the Sunday's magnetic field and pushes outward, making it harder for cosmic rays to penetrate deeply into the solar system. During these times, fewer cosmic rays reach Earth. When solar activity is low, the solar wind weakens and the Sunday's magnetic field becomes less chaotic, allowing more cosmic rays to enter. This creates a clear cycle where cosmic ray levels are highest during solar minimum and lowest during solar maximum. The path of cosmic rays is also influenced by the way magnetic fields twist and shift. As they travel through space, charged particles do not move in straight lines through a magnetic field. Instead, they spiral and scatter, often taking complex routes before reaching Earth. When the Sunday's magnetic field is strong and tangled, it deflects many cosmic rays or traps them in certain regions. This process can create uneven patterns, with some areas receiving more cosmic rays than others. A helpful way to imagine this is to think of leaves floating down a river. If the river flows smoothly, the leaves move straight downstream. If there are whirlpools and currents, the leaves spin, slow down, or get caught in eddies. The Sunday's magnetic field acts like those shifting currents, constantly changing the paths of incoming cosmic rays. Sudden solar events, such as flares or coronal mass ejections, can cause sharp, temporary drops in cosmic ray levels. These drops, called Forbush decreases, happen when a burst of solar particles sweeps through space and pushes cosmic rays aside. After the burst passes, cosmic ray levels slowly return to normal. By tracking these changes, scientists can learn about the structure of the solar wind and how it interacts with the galaxy beyond. Understanding cosmic ray interactions is important for space travel and technology. High-energy cosmic rays can damage spacecraft electronics and pose health risks to astronauts. By studying how the Sunday's activity shapes cosmic ray patterns, scientists can better predict when and where these particles will be most intense. Spacecraft like Voyager and Parker Solar Probe are helping to map these interactions, providing new insights into how the Sunday shields the solar system from the constant rain of cosmic particles coming from deep space. Geomagnetic storms occur when charged particles from the Sunday interact with Earth's magnetic field. These storms can disrupt satellites, power grids, and communication systems. Most storms follow a predictable pattern. They are usually caused by large solar events such as flares or coronal mass ejections, where massive amounts of plasma and magnetic energy are released into space. Scientists can often track these events using solar observatories and warn of incoming disturbances. However, there are times when geomagnetic storms happen suddenly, without any clear trigger. These unexpected events remain one of the puzzles in space weather science. In a typical case, a visible eruption on the Sunday sends a wave of particles toward Earth. Instruments detect the eruption, and models predict when the particles will arrive. With sudden storms, no obvious eruption is seen. The solar surface may look calm, with few sunspots or flares, yet Earth's magnetic field can still experience a sharp and intense disturbance. This makes forecasting difficult and leaves little time to protect sensitive systems on the ground or in orbit. Lone possible explanation involves smaller-scale solar events that are too subtle to detect easily. The Sunday's surface is filled with constant magnetic activity, much of it hidden beneath the visible layers. Tiny magnetic reconnection events could release bursts of energy that escape into space without creating dramatic visual signs. These bursts might combine as they travel outward, forming a stream of particles strong enough to trigger a storm when it reaches Earth. Because these events happen below the limits of many instruments, they remain invisible until their effects are felt. Another idea focuses on structures in the solar wind itself. Even without a major eruption, the solar wind is not uniform. It contains fast and slow streams that weave together, creating boundaries where particles interact. If two streams collide, the result can be a shock wave that intensifies the flow of particles toward Earth. This can happen far from the Sunday, making it hard to trace back to a clear source. The effect is similar to weather on Earth, where a storm can form suddenly when warm and cold air masses meet. Even if the sky was clear earlier, Earth's own magnetic field may also play a role. Certain configurations of the field can make it more vulnerable to incoming solar particles. If the field lines are aligned in a particular way, even a modest flow of particles can slip through and cause a large reaction. This is like a door that swings open easily when pushed from the right angle. Spacecraft, such as the Parker Solar Probe and satellites in Earth's orbit, are now gathering data to study these hidden processes. By tracking the solar wind more closely and mapping how Earth's field responds, scientists hope to understand why some storms strike without warning. Solving this mystery would improve space weather forecasting and reduce the risk to technology and infrastructure that depend on reliable predictions. The Sunday's activity rises and falls in a repeating pattern that lasts about 11 years. This cycle is most visible through changes in sunspots, which are dark regions on the Sunday's surface caused by strong magnetic fields. During solar maximum, many sunspots appear, and the Sunday produces more flares and eruptions. During solar minimum, sunspots are scarce, and the Sunday becomes quieter. While this cycle has been observed for centuries, its intensity is not always the same. Some cycles are very strong, with large numbers of sunspots and powerful events, while others are weak. Over centuries, these variations form long-term trends that scientists are still trying to explain. Historical records show that solar activity has gone through extreme changes. Between the mid-1600s and early 1700s, there was a period called the Maunder Minimum, when almost no sunspots were seen for several decades. During this time, parts of Earth experienced cooler climates, suggesting a link between solar activity and conditions on our planet. At other times, solar cycles have been unusually intense, with large numbers of sunspots and strong solar storms. These long-term changes do not follow a simple pattern, which makes them difficult to predict. The Sunday's magnetic field drives the solar cycle. It is generated by the motion of charged plasma inside the Sunday, through a process called the solar dynamo. The field twists and stretches as the Sunday rotates, and as plasma flows rise and fall in the convection zone. Over time, the magnetic field becomes tangled and complex, then reorganizes and flips, starting a new cycle. Small differences in how the plasma moves or how the magnetic fields interact may gradually build up, causing some cycles to be stronger or weaker than others. External factors might also play a role. The Sunday moves through different regions of the galaxy, and the surrounding interstellar environment changes. Variations in external magnetic fields or nearby clouds of gas could affect the outer layers of the Sunday and subtly alter its behavior over long timescales. Although this idea is still being explored, it may help explain some of the irregularities seen in historical records. Scientists also study how layers deep inside the Sunday might store magnetic energy over several cycles. If this stored energy is released slowly, the next cycle might be weak. If it is released quickly, the following cycle could be much stronger. This would be similar to a reservoir filling and emptying at different rates, depending on how much water flows into it. Modern spacecraft like the Solar Dynamics Observatory and the Parker Solar Probe are collecting data to track these processes in real time. By comparing current solar activity with historical patterns, researchers hope to understand why the Sunday cycles change so dramatically over centuries. This knowledge is important because the Sunday's long-term behavior influences space weather, which can affect satellites, power grids, and even climate patterns on Earth. Between about 1645 and 1715, the Sunday went through an unusual phase known as the Maunder Minimum. During this period, the number of sunspots dropped dramatically. For decades, observers recorded almost no sunspots, even though they had been tracking them regularly before and after this time. Normally, the Sunday follows an 11-year cycle in which sunspots increase and decrease in a predictable rhythm. The Maunder Minimum broke that pattern, leaving scientists with a mystery that still has no clear answer. Historical records show that this period coincided with colder climates on Earth, especially in parts of Europe and North America. Rivers like the Thames in London froze during winters, and glaciers advanced in some regions. This time of cooler conditions is sometimes called the Little Ice Age. While the link between solar activity and climate is complex, the timing suggests that the unusually quiet Sunday may have played a role. With fewer sunspots, the Sunday was likely producing less energy overall, though the exact amount of reduction remains debated. One possible explanation is that the Sunday's magnetic field weakened or changed in a way that disrupted the normal solar cycle. Sunspots are caused by strong magnetic fields pushing through the Sunday's surface. If the processes that generate these fields slowed or became unstable, sunspots would not form in their usual numbers. The Sunday's magnetic field is driven by the motion of plasma in the convection zone, where hot material rises and cooler material sinks. Changes in the speed or pattern of this motion could have altered the way the field was built and maintained. Some scientists suggest that random variations within the solar dynamo could explain the Maunder Minimum. Just as weather on Earth can shift between calm and stormy periods, without a single cause, the Sunday's internal flows may sometimes settle into a quiet state on their own. This idea is supported by computer models that show the solar cycle can naturally fluctuate over long timescales. External influences are also considered. The Sunday moves through different parts of the galaxy, encountering varying amounts of gas, dust, and magnetic fields. These external factors might subtly affect the outer layers of the Sunday or its magnetic behavior. While there is no direct evidence for this during the Maunder minimum, it remains an area of active study. Researchers continue to examine ice cores, tree rings, and other natural records that capture traces of solar activity. These records contain chemical signatures, such as certain isotopes, that increase when cosmic rays reach Earth. Since the Sunday's magnetic field blocks some cosmic rays, higher levels of these isotopes mean the Sunday was less active. Data from these sources confirm that the Maunder minimum was a real and unusual drop in solar activity. Although centuries have passed, the cause of this quiet period remains uncertain. By studying the Sunday today and comparing it with these historical clues, scientists hope to uncover what triggered this rare and dramatic pause in the solar cycle. The Sunday goes through a repeating cycle of activity that lasts about 11 years. During this time, the number of sunspots rises and falls in a predictable pattern. The peak of this cycle, called solar maximum, is when sunspots, flares, and eruptions are most frequent and intense. These events can affect satellites, power grids, and communications on Earth. So predicting when a solar maximum will occur is important. Despite decades of study, scientists cannot reliably forecast the exact timing or strength of these peaks years in advance. The challenge comes from the Sunday's complex magnetic behavior. Sunspots are surface signs of powerful magnetic fields generated deep inside the Sunday. These fields are created by moving plasma in a process called the solar dynamo. The plasma rises, sinks, and shifts as the Sunday rotates. Its equator spins faster than the poles, stretching and twisting the magnetic field lines. Over time, this builds up tangled fields that eventually reorganize and flip, creating a new solar cycle. The problem is that these motions are chaotic and hidden beneath the surface, making them very difficult to measure directly. Current forecasts rely on observing patterns at the start of a new cycle and comparing them to past cycles. For example, the number and location of early sunspots can give hints about how strong the cycle might become. However, these signals are often unreliable. Two cycles that look similar at the beginning can turn out very differently. Some cycles grow quickly and reach high levels of activity while others stay weak. This is like trying to predict the size of a storm by looking only at the first few clouds. Another difficulty is that the Sunday may store magnetic energy over several cycles. A weak cycle might be followed by a much stronger one if extra energy is released. This hidden buildup is invisible until it shows itself on the surface. It's as if a river's flow depended not just on the current rainfall, but also on underground reservoirs that fill and empty at unpredictable times. Computer models of the solar dynamo help scientists test ideas and simulate future cycles. These models can recreate the general shape of the cycle, but they are still too simple to capture all the fine details. Small changes in the Sunday's interior can lead to very different outcomes, making long-term forecasts uncertain. Even with powerful supercomputers, these models cannot yet predict exactly when a peak will happen or how intense it will be. As a result, forecasts are most accurate only a year or two before the actual maximum. Space agencies and observatories monitor the Sunday closely, looking for signs that activity is increasing. Once the cycle is clearly underway, predictions improve. Until then, the timing and strength of solar maxima remain one of the most challenging problems in space weather science, leaving scientists to work with probabilities rather than precise forecasts. The solar wind is a continuous flow of charged particles that streams outward from the Sunday into space. It fills the solar system and shapes the space environment around planets. Spacecraft have measured two distinct types of solar wind, a fast stream and a slow stream. The fast solar wind can reach speeds of more than 800 kilometers per second, while the slow solar wind moves at about 300 to 500 kilometers per second. These two speeds have been observed for decades, but scientists are still trying to understand why they exist and how they are produced. The fast solar wind is closely linked to coronal holes, which are dark regions in the Sunday's outer atmosphere. In these areas, magnetic field lines are open rather than looping back into the Sunday. This open structure allows particles to flow outward freely. As a result, the plasma escapes quickly and accelerates to high speeds. Coronal holes are most common near the Sunday's poles during periods of low solar activity, so the fast solar wind tends to flow steadily from these regions for months at a time. When Earth crosses one of these streams, it can experience enhanced space weather, including strong auroras and disturbances to satellites. The slow solar wind is more complicated. It often comes from regions near the Sunday's equator, where magnetic fields are tangled and closed. In these regions, plasma is trapped in loops and cannot escape easily. Somehow, some of the plasma still finds a way out, but it moves more slowly and less consistently than in coronal holes. One idea is that magnetic reconnection plays a role. When magnetic loops break and reconnect, they may release small bursts of plasma into space, creating a slow, variable stream. Another possibility is that waves moving through the Sunday's atmosphere gradually push particles outward, but with less force than in the fast wind. The boundary between fast and slow wind regions can be sharp, almost like a weather front on Earth. Spacecraft passing through this boundary detect sudden changes in speed, density, and temperature. These transitions suggest that the two types of solar wind are produced by very different processes. Sometimes, fast and slow streams collide as they travel outward, creating shock waves that can intensify space weather effects near Earth. To picture the difference, imagine water flowing from a wide open hose compared to water seeping through a clogged filter. The open hose represents the fast solar wind from coronal holes, while the clogged filter represents the tangled magnetic regions where the slow wind originates. NASA's Parker Solar Probe and other missions are now gathering data closer to the Sunday than ever before. These observations are helping scientists track the solar wind back to its source and reveal how magnetic structures shape its speed. Understanding why the Sunday produces two distinct wind streams will improve predictions of space weather and help protect technology on Earth and in space. Coronal mass ejections, or CMEs, are huge bursts of plasma and magnetic fields that erupt from the Sunday's outer atmosphere and travel through space. They can contain billions of tons of charged particles and move at millions of kilometers per h. When a CME heads toward Earth, it can disrupt satellites, power grids, and communication systems. Scientists can track CMEs once they occur, but predicting exactly when they will happen remains one of the most difficult problems in solar physics. CMEs are closely tied to the Sunday's magnetic activity. The Sunday's surface is covered with magnetic field lines created by the motion of plasma beneath it. These field lines twist, stretch, and tangle as the plasma moves. Sunspots form where magnetic fields are especially strong. In these regions, energy builds up over time as the field lines become more complex. At some point, the magnetic structure becomes unstable and suddenly releases its stored energy, launching a CME. The challenge is knowing when that breaking point will be reached. One idea is that CMEs are triggered by magnetic reconnection. This process occurs when two sets of magnetic field lines cross and snap into new positions. When reconnection happens on a large scale, it can release massive amounts of energy very quickly, enough to propel plasma into space. Scientists can sometimes detect small signs of reconnection just before a CME, but these signals are subtle and not always present. It's like trying to predict when a stretched rubber band will snap. It will happen eventually, but not the exact moment. The build-up to a CME can take days or even weeks. Magnetic loops grow more twisted as plasma flows push and pull on them. During this time, the surface may appear calm, giving no clear warning. A region can stay stable for a long period, and then erupt suddenly without any obvious trigger. This unpredictability makes it difficult to forecast CME timing with precision. The Sunday's overall activity level also plays a role. During solar maximum, when sunspots and flares are common, CMEs occur more frequently. However, they can still happen during quieter periods, which adds another layer of complexity. The difference may lie in how the magnetic fields are arranged. Large, organized fields tend to produce bigger, more dramatic eruptions, while smaller, scattered fields may create weaker or slower CMEs. To better understand these events, spacecraft like NASA's Solar Dynamics Observatory and Parker Solar Probe watch the Sunday in detail, capturing images of its surface and outer atmosphere. These observations help scientists track how magnetic energy builds up and changes over time. A useful way to picture the process is to think of snow building on a mountain slope. For a long time, the snow piles up quietly. Then, a small shift, perhaps even a tiny movement, triggers an avalanche. In the same way, the Sunday's magnetic fields store energy until a sudden change causes it to release in a massive eruption that races across the solar system. Most solar storms begin with clear signs on the Sunday's surface. A large sunspot cluster might grow over several days. Magnetic fields may become twisted and unstable, and bright flashes called solar flares can signal that an eruption is about to happen. These events give scientists a way to anticipate when a storm will form and how strong it might be. However, not all solar storms follow this pattern. Some occur suddenly, without any visible warning, and reach Earth before anyone can prepare. These unpredictable storms remain one of the biggest challenges in space weather forecasting. A solar storm happens when the Sunday releases a surge of charged particles and magnetic energy into space. The most powerful events involve coronal mass ejections, or CMEs, which are massive bursts of plasma and magnetic fields. When a CME collides with Earth's magnetic field, it can trigger geomagnetic storms that disrupt satellites, power grids, and communication systems. Normally, scientists can track a CME from the moment it leaves the Sunday until it reaches Earth. The difficulty comes when no visible eruption is seen, yet a surge of solar particles still arrives. One possibility is that these storms begin deep within the Sunday's atmosphere, where magnetic changes are hidden from view. The Sunday's surface is covered with countless magnetic field lines that rise and fall as plasma moves below. In some regions, the fields may tangle and reconnect on a small scale, releasing energy without producing the bright flashes that instruments usually detect. The resulting burst of particles may escape quietly and travel toward Earth with little warning. By the time the particles are detected by spacecraft near our planet, the storm is already underway. Another explanation is that the solar wind itself sometimes creates disturbances far from the Sunday. The solar wind is not uniform. It flows at different speeds and densities, and these streams can collide as they move outward. When a fast stream catches up to a slower one, it can form a shock wave that intensifies the flow of particles toward Earth. This type of storm may form well beyond the reach of solar observatories, leaving no surface trace to study. It is similar to weather on Earth, where a storm can form suddenly, when two air masses meet, even if the sky above was clear only hours earlier. The orientation of Earth's magnetic field can also affect how severe a storm becomes. If the solar particles arrive at just the right angle, they can slip past the planet's defenses and cause a strong reaction. Even a modest burst of particles can lead to a powerful storm if conditions align in this way. To track these hidden processes, missions like NASA's Parker Solar Probe and other space-based observatories are measuring the solar wind closer to its source than ever before. Their data may reveal the subtle signals that precede these silent eruptions. Until then, some solar storms will remain unpredictable, appearing without warning and challenging our ability to protect technology and systems on Earth. The Sunday's brightness, or luminosity, comes from the nuclear fusion reactions in its core. These reactions turn hydrogen into helium, releasing energy that travels outward before it finally shines as sunlight. Over billions of years, the Sunday's energy output has slowly increased. And this trend will continue. Scientists can estimate the general pattern of this change, but predicting the exact rate is more difficult. Small uncertainties in the Sunday's structure and behavior make precise forecasts challenging. As the Sunday fuses hydrogen into helium, the amount of hydrogen in the core decreases. Helium, which is denser, builds up and causes the core to contract slightly. This contraction raises the temperature and pressure, making fusion happen faster. A faster fusion rate produces more energy, which increases the Sunday's luminosity. Current models suggest the Sunday is about 30% brighter today than it was when it first formed around 4.6 billion years ago. Over the next billion years, its brightness will continue to rise slowly, but the exact timeline depends on details deep inside the core that are difficult to measure directly. One uncertainty comes from how evenly the core mixes. If hydrogen is stirred and spread out, fusion can continue smoothly for a long time. If the core is more stratified, with clear boundaries between layers, some regions might run out of fuel sooner, changing the pace of energy production. This mixing happens on scales that are hard to observe, so scientists rely on indirect clues such as vibrations within the Sunday, measured through helioseismology. Another factor is how changes in the outer layers might affect the flow of energy. The Sunday's convection zone moves heat outward through rising and sinking currents of plasma. Small variations in how this zone behaves could influence how efficiently energy escapes, slightly altering the total brightness we see. Even minor differences add up over millions of years, so models must account for these processes with care. To understand how this works, imagine a campfire that slowly grows as more wood is added. If you know how much wood is left and how quickly it burns, you can predict when the fire will grow brighter. But if the wood is packed unevenly or burns at varying rates, the fire's brightness will change in ways that are harder to predict. The Sunday works in a similar way, with its fuel and heat transfer, creating complex patterns over time. Eventually, in about 5 billion years, the Sunday will run out of hydrogen in its core. At that point, its brightness will increase dramatically as it expands into a red giant. Before that stage, however, the gradual brightening will continue at a pace that affects Earth's climate and habitability. While the broad outline of this evolution is clear, pinpointing the exact rate of change remains an ongoing challenge that requires combining theory, computer models, and continuous observations of our star. The Sunday is an enormous ball of plasma, containing almost all the mass in the solar system. With so much material, it should spin very quickly if it kept all the angular momentum it had when it formed. Angular momentum is the property that keeps spinning objects moving unless something slows them down. When the solar system began as a giant cloud of gas and dust, that cloud rotated as it collapsed under gravity. As the material moved inward, it spun faster, much like a figure skater pulling in their arms. By this reasoning, the Sunday should have been left spinning at a very high rate. Instead, today it rotates slowly, taking about 25 days to complete a turn at the equator. This mismatch is a puzzle scientists have been working to explain. One possible answer lies in the solar wind. The Sunday constantly sheds charged particles into space, and these particles interact with its magnetic field. As the particles stream outward, they can drag on the Sunday's outer layers. Over billions of years, this magnetic braking could have gradually bled away the Sunday's rotational energy. The effect is similar to a spinning wheel in water, slowing down as the water resists its motion. The challenge is that calculations show the solar wind alone might not be strong enough to account for the amount of slowing observed. The early Sunday may have had a much stronger magnetic field than it does now. In its youth, the Sunday was more active, with frequent eruptions and intense magnetic activity. A powerful magnetic field would have created a stronger link between the Sunday and the solar wind, allowing more angular momentum to be lost at a faster rate. As the Sunday aged and its magnetic field weakened, the braking would have slowed, leaving the Sunday spinning at its present pace. Observations of young stars in other systems support this idea, as many of them rotate quickly, but show signs of slowing down over time. Another factor may involve the Sunday's interaction with the disk of gas and dust from which the planets formed. During the early stages, magnetic forces could have connected the Sunday's outer layers to the surrounding disk. This connection might have acted like a brake, transferring angular momentum from the Sunday to the disk material. That extra momentum could then have been carried away as planets and smaller bodies formed. This would help explain why the planets, especially Jupiter and Saturn, hold a large share of the solar system's total angular momentum, even though they contain only a small fraction of its mass. To picture this process, imagine a spinning potter's wheel connected by a rope to another wheel. If the second wheel starts moving, it can slow down the first as energy transfers between them. In the same way, magnetic connections between the young Sunday and its disk may have slowed the Sunday's rotation. Understanding exactly how these mechanisms worked is key to explaining why our star spins as slowly as it does today. The Sunday is not fixed in space. It moves through the Milky Way galaxy, orbiting its center at an average speed of about 828,000 kilometers per h-hour. Even at this incredible pace, a single orbit takes around 230 million years to complete. As the Sunday travels, it carries the entire solar system with it, including Earth and the other planets. This journey is shaped by gravity, magnetic fields, and the interstellar material that fills the galaxy. The motion is smooth on large scales, but along the way, the Sunday encounters regions that may influence its behavior, and in turn, affect the solar system. The Sunday's path takes it through areas of the galaxy with different densities of gas, dust, and cosmic rays. These regions are not evenly distributed. Some parts of the galaxy are relatively empty, while others are crowded with thick clouds of gas and debris from past generations of stars. When the Sunday moves through a more crowded region, the heliosphere, which is the bubble of charged particles and magnetic fields created by the solar wind, can be compressed. In quieter regions, the heliosphere expands outward. This change in size alters how well the solar system is shielded from cosmic rays, which are high-energy particles that come from supernovae and other powerful events in the galaxy. When the heliosphere is smaller, more cosmic rays reach the inner solar system, including Earth. These particles can interact with the atmosphere and even leave chemical traces in ice cores and tree rings. By studying these traces, scientists can reconstruct parts of the Sunday's past journey and see how its motion through the galaxy might have influenced conditions on our planet. Some researchers suggest that periods of higher cosmic ray exposure could be linked to changes in Earth's climate, or even to biological effects. though this connection is still being studied. The Sunday's magnetic field also interacts with the galactic environment. As it moves, it encounters external magnetic fields that can press against the heliosphere and shape its structure. Data from the Voyager spacecraft, which have traveled beyond the edge of the heliosphere, show that this boundary is not smooth. Instead, it is irregular and shaped by both the outward pressure of the solar wind and the inward push of the interstellar medium. These distortions may influence how solar particles escape into space and how galactic particles enter, creating complex patterns of interaction. The Sunday's motion is not constant over time. It wobbles slightly as it orbits, moving up and down relative to the flat disk of the galaxy. This vertical motion happens on a cycle of about 60 million years. Each time the Sunday crosses the galactic plane, it may pass through regions with higher densities of gas and stars. These crossings could expose the solar system to increased cosmic rays or gravitational forces. Some theories suggest that these encounters might coincide with patterns seen in Earth's geological record, such as mass extinctions or periods of increased comet activity. Though the evidence remains debated, another aspect of the Sunday's motion is its interaction with nearby stars and stellar clusters. Over millions of years, the distances between stars change as they move along their own orbits. Occasionally, a star may pass close enough to disturb the Oort cloud, a vast region of icy bodies at the edge of the solar system. A strong gravitational nudge could send comets tumbling inward toward the inner planets. These interactions are rare on human timescales, but may happen several times during the Sunday's long journey around the galaxy. If a large number of comets were sent inward at once, it could lead to an increase in impacts on Earth and other planets. The solar system's motion also determines the direction from which interstellar particles flow toward the Sunday. Instruments on spacecraft like the Interstellar Boundary Explorer, IBEX, have detected streams of neutral atoms entering the heliosphere. These particles provide clues about the environment outside our solar system. As the Sunday moves, the pattern and intensity of these incoming particles change, revealing how different regions of space vary in density and composition. To picture the Sunday's motion, imagine a boat traveling across a vast ocean. The boat creates its own wake, just as the solar wind shapes the heliosphere. As the boat moves, it passes through areas with calm water and areas with strong currents. These external forces push and reshape the wake, changing how it interacts with the water around it. In the same way, the Sunday's movement through the galaxy changes how it interacts with the interstellar medium, sometimes compressing the heliosphere and sometimes allowing it to expand. The Parker Solar Probe and other missions studying the Sunday are providing new data about how the solar wind behaves and how it responds to external conditions. Combined with data from Voyager and IBEX, scientists are building models to understand the link between the Sunday's galactic environment and its activity. These models suggest that as the Sunday encounters regions with different magnetic and particle pressures, its own magnetic behavior may shift slightly. Even small changes could influence the timing and strength of solar cycles, affecting space weather throughout the solar system. Over very long timescales, the Sunday's journey may help explain some of the variations seen in solar activity and its effects on Earth. While the day-to-day behavior of the Sunday is driven by processes inside its core and outer layers, the larger environment through which it travels provides an ever-changing backdrop. By tracing the Sunday's path and studying the galactic regions it has passed through, scientists hope to understand how the motion of our star shapes both its activity and the conditions experienced by the planets that orbit it. Astronomers have identified many stars in our galaxy that are very similar to the Sunday. These stars, called solar twins, share nearly the same size, temperature, and chemical composition. Studying them helps scientists understand how the Sunday fits into the broader population of stars. Surprisingly, when these solar twins are observed, many of them appear far more active than the Sunday. Their surfaces show stronger magnetic fields, brighter flares, and more frequent eruptions. This raises a puzzle. Why does our Sunday seem calmer than stars that are almost identical to it? The difference is most obvious when looking at star spots, which are similar to sunspots. Star spots form where magnetic fields block heat from rising, creating dark patches on the surface. Many solar twins show large star spots that cover a much greater area than the Sunday's sunspots. This suggests that their magnetic activity is higher overall. If the Sunday behaved in the same way, space weather near Earth would be far more intense, with stronger solar flares and more frequent disruptions to satellites and communications. Zone possible explanation is age. Stars slow their rotation as they grow older, and rotation plays a key role in driving magnetic activity. Younger stars spin faster, which stirs their internal plasma more vigorously and generates stronger magnetic fields. If many of the solar twins studied are slightly younger than the Sunday, their higher activity could simply reflect this difference in age. Over time, as they lose rotational energy through their stellar winds, their magnetic activity may settle down to levels similar to the Sunday's. However, some of the stars with strong activity are very close in age to the Sunday, which suggests there may be other factors at work. The composition of a star can subtly affect how its magnetic field forms and evolves. Even small differences in the amounts of elements like iron or carbon can influence how heat moves through the star's outer layers. These variations might lead to different magnetic behaviors, even among stars that seem nearly identical on the surface. Another idea involves long-term cycles. The Sunday follows an 11-year solar cycle, with periods of high and low activity. It is possible that other stars have cycles too, but on much longer or more irregular timescales. If a star was observed during a peak in its cycle, it would appear more active, while another star in a quiet phase might seem calm. This makes it difficult to compare stars based on short-term observations. To understand the differences more clearly, astronomers monitor solar twins over many years, looking for patterns in their brightness and magnetic behavior. By comparing these stars to our Sunday, scientists hope to learn whether the Sunday's calmness is unusual or simply a phase in a much longer cycle. The answer will reveal whether our star is truly special or just one example of the many ways stars like it can behave. Over 4.5 billion years ago, the solar system began as a vast cloud of gas and dust drifting in space. Gravity caused parts of this cloud to clump together, forming denser regions that pulled in more material. At the center of one of these regions, the Sunday began to form. As the young Sunday grew, the rest of the cloud flattened into a rotating disk. This protoplanetary disk became the birthplace of planets, moons, asteroids, and comets. While the overall process is understood, the exact role of the Sunday's early radiation in shaping this disk is still unclear. These early emissions were far stronger than what the Sunday produces today. The radiation would have interacted with the surrounding gas and dust in complex ways. High-energy ultraviolet light could heat the disk's upper layers, causing some of the gas to evaporate and escape into space. This process might have helped clear material from certain regions, affecting where planets could form and what they were made of. The inner part of the disk, close to the Sunday, would have been especially vulnerable to this heating. Some models suggest that strong radiation could have stripped away lighter gases like hydrogen and helium, leaving heavier elements behind. This may explain why the inner planets, such as Earth and Mars, are rocky rather than gas giants, like Jupiter and Saturn. However, direct evidence for how much radiation was involved and how fast this clearing happened is still lacking. At the same time, the young Sunday's magnetic field and solar wind may have influenced the disk's motion. Charged particles streaming outward could have carried away material or stirred it, altering the way dust grains stuck together to form larger bodies. These forces might have created gaps or pressure differences in the disk, shaping how matter collected into planets. Modern telescopes have observed similar patterns in disks around other young stars. But each system appears slightly different, making it hard to apply these findings directly to our own history. One difficulty in solving this puzzle is that the early solar system has long since disappeared. The gas and dust that made up the protoplanetary disk were either swept away or incorporated into planets and other objects. Scientists rely on indirect clues, such as studying meteorites. These ancient rocks preserve chemical signatures that hint at the conditions in the early disk. Certain isotopes show signs of exposure to intense radiation, suggesting that the Sunday's light and particles played a major role during the solar system's first few million years. To visualize this process, imagine a shallow pool of water under a hot sun. As the sunlight grows stronger, parts of the water evaporate while other areas remain cooler and untouched. Over time, the pattern of evaporation shapes the pool's surface. In a similar way, the Sunday's early radiation may have sculpted the protoplanetary disk, guiding the growth and arrangement of the planets we see today. The Sunday's composition is mostly hydrogen and helium, with small amounts of heavier elements such as oxygen, carbon, neon, and iron. These elements, called metals in astronomy, give scientists important clues about how the Sunday and the solar system formed. Standard models predict how much of each element should be present based on how stars form and evolve. However, when researchers study the Sunday's light using spectroscopy or analyze samples from the solar wind, they find certain elements are more abundant than expected. These mysterious chemical anomalies suggest that something about the Sunday's formation or internal processes is not fully understood. Lone striking example involves neon. Measurements of the solar wind and certain regions of the Sunday's atmosphere show higher levels of neon than models predict. The problem is difficult to study because neon does not produce clear spectral lines in the visible range. So direct measurements are limited. This makes it challenging to confirm exactly how much neon the Sunday contains. Yet the available data strongly suggest that our current models underestimate its abundance. If true, this would mean that the basic assumptions about how elements are transported inside the Sunday need to be reconsidered. Other elements show similar puzzles. Some metals appear in greater amounts in the Sunday's outer layers than deep inside, while others show the opposite. This uneven distribution is not fully explained by standard theories of convection, which describe how material moves between layers in the Sunday. For instance, convection should mix the outer layers thoroughly, leading to a smooth and even spread of elements. Instead, observations reveal subtle but persistent differences. This suggests that additional forces such as magnetic fields or waves might be influencing how elements move and settle over time. These anomalies also appear when comparing the Sunday to other stars. Most stars similar to the Sunday follow predictable patterns of composition, yet our Sunday shows certain deviations. This raises questions about whether something unusual happened during the Sunday's birth. Perhaps the cloud of gas and dust that formed the solar system was enriched by a nearby supernova or other event, adding extra amounts of certain elements. If so, the Sunday's unique chemical fingerprint would reflect this special origin. Meteorites provide another source of evidence. These ancient rocks preserve the original material from the early solar system. Their composition can be compared to that of the Sunday to check for differences. In some cases, the ratios of certain isotopes in meteorites do not match what is seen in the Sunday today. This mismatch suggests that some process either inside the Sunday or during the solar system's formation changed the distribution of elements over time. To picture this, imagine stirring sugar into a cup of tea. If the tea is stirred evenly, the sugar spreads out smoothly. But if the stirring is uneven or other forces act on the liquid, some areas will end up sweeter than others. In a similar way, the Sunday's elements have not mixed in the simple, uniform way models predict. leaving scientists searching for the hidden processes behind these chemical anomalies. The Sunday is the main source of energy for Earth's climate system. Its light and heat drive winds, ocean currents, and the water cycle. Changes in solar activity can therefore influence climate. But the exact connection is complex. Solar activity rises and falls in cycles, most notably the 11-year solar cycle, marked by the appearance and disappearance of sunspots. During periods of high activity, the Sunday emits slightly more energy and produces more ultraviolet radiation and solar wind. These variations are small compared to the Sunday's total output, but they can have measurable effects on Earth's atmosphere. One way solar activity affects climate is through changes in ultraviolet radiation. UV light interacts strongly with the upper atmosphere, especially the ozone layer. When UV levels increase, they can alter patterns of temperature and circulation high above Earth. These changes can then influence weather lower down, similar to how shifts in the jet stream affect conditions on the ground. This process is indirect and depends on many factors, which makes it difficult to predict precisely how a change in UV output will affect climate in a specific region. The solar wind also plays a role by interacting with Earth's magnetic field. When solar activity is high, the stronger solar wind helps shield Earth from some cosmic rays, which are high-energy particles from space. Some scientists propose that cosmic rays may affect cloud formation by helping tiny particles in the atmosphere gather water droplets. If solar activity reduces the number of cosmic rays reaching Earth, cloud cover might change, altering how much sunlight is reflected back into space. This idea is still debated, because the effect, if it exists, appears to be subtle and difficult to separate from other influences on clouds. Historical records show that long periods of low solar activity have coincided with cooler climates on Earth. The Maunder minimum in the late 1600s, when sunspots almost vanished for decades, overlapped with part of the Little Ice Age, a time of colder temperatures in Europe and North America. This suggests a connection, but it does not mean solar activity was the only factor. Volcanic eruptions, changes in ocean currents, and natural climate cycles also contributed to the cooling during that period. Distinguishing the Sunday's role from these other factors remains a challenge. In modern times, measurements show that changes in the Sunday's output over the last century have been small compared to the effects of greenhouse gases. While solar activity still influences short-term variations in climate, such as regional temperature shifts and atmospheric patterns, it cannot explain the rapid global warming seen in recent decades. A helpful way to think about it is to imagine a campfire and a blanket. The Sunday's variations are like the fire flickering slightly brighter or dimmer, while greenhouse gases act like adding extra layers of blankets that trap heat. Understanding both effects together is essential for building accurate climate models and predicting how Earth's climate will evolve. The Sunday exists in a delicate state of balance. At its core, nuclear fusion reactions turn hydrogen into helium, releasing a vast amount of energy. This energy pushes outward, creating pressure that tries to make the Sunday expand. At the same time, gravity pulls inward, trying to make the Sunday collapse under its own immense weight. The Sunday remains stable because these two forces are matched so precisely. This balance is called hydrostatic equilibrium, and it has kept the Sunday shining steadily for billions of years. Deep inside the Sunday, the temperature and pressure are extreme. The core reaches about 15 million degrees Celsius, hot enough for hydrogen nuclei to overcome their natural repulsion and fuse together. Each fusion reaction releases energy in the form of light and heat. The sheer number of these reactions creates an outward push, strong enough to counteract the crushing pull of gravity. If fusion slowed even slightly, gravity would gain the upper hand, causing the core to contract. This contraction would increase the temperature and pressure, which would in turn speed up fusion until the outward push rose back to match gravity again. In this way, the Sunday naturally regulates itself. If fusion increased too much, the opposite would happen. The extra outward pressure would cause the core to expand. As it expanded, the temperature and pressure would drop, slowing the fusion reactions. This built-in feedback system ensures that the Sunday does not burn out too quickly or collapse suddenly. It is like a thermostat that keeps a room at a steady temperature, adjusting automatically when conditions change. The balance extends beyond the core. Energy from fusion moves outward through the layers of the Sunday, first by radiation, then by convection as hot plasma rises and cooler plasma sinks. This process takes thousands to millions of years, but it keeps the flow of energy smooth and steady. By the time the energy reaches the surface and escapes as sunlight, the variations are so small that Earth receives a nearly constant supply of light and heat. A simple analogy can help explain this balance. Imagine filling a balloon with air while squeezing it tightly in your hands. The air inside pushes outward, while your hands push inward. If you add too much air, the outward force grows, and you have to squeeze harder to keep it from escaping. If you loosen your grip, the balloon expands and the pressure inside drops. The Sunday works the same way, except that gravity acts like your hands and fusion acts like the air pushing out. The two forces remain locked in equilibrium. Over billions of years, as hydrogen is gradually converted to helium, the Sunday will adjust to keep this balance. Its core will slowly contract and heat up, causing fusion to increase and the outer layers to expand. For now, the forces are so well matched that the Sunday remains steady, providing the stable energy needed to support life on Earth. The Sunday is halfway through its life. For billions of years, it has steadily fused hydrogen into helium in its core, releasing the energy that lights and warms the solar system. Eventually, the hydrogen in the core will run out. When that happens, the balance between gravity pulling inward and fusion pushing outward will shift. Gravity will begin to squeeze the core, increasing its temperature and pressure. This will cause the outer layers of the Sunday to expand, and the Sunday will become a red giant. At this stage, its outer atmosphere will grow so large that it may engulf Mercury and Venus and possibly Earth. During the red giant phase, the Sunday will start fusing helium into heavier elements like carbon and oxygen. These reactions will occur in shells around the core and in unstable bursts. The energy released will make the Sunday swell and contract repeatedly. As this process continues, the outer layers will be lost into space, forming a glowing shell of gas known as a planetary nebula. This material will eventually drift away, leaving the core behind. What remains will be the Sunday's final state, a white dwarf, a small dense object, roughly the size of Earth, but containing much of the Sunday's original mass. While this general outline is well understood, the exact way the Sunday will make this transition is still uncertain. One mystery is how quickly the outer layers will be shed. Some models suggest a slow, steady loss of material over millions of years, while others predict more dramatic and sudden ejections. The timing and violence of this process will affect the shape and brightness of the planetary nebula that forms. Observations of other stars show many different outcomes, from smooth, symmetrical shells to complex, twisted structures. Scientists do not yet know which pattern the Sunday will follow. Another question concerns what happens inside the core as it cools. A white dwarf does not produce energy through fusion. Instead, it shines with leftover heat, which slowly fades over billions of years. The exact mix of carbon and oxygen in the Sunday's core will determine how it cools and how it behaves as it solidifies. If the balance between these elements is slightly different than models predict, the cooling process might take a very different path. This could affect the timing of the Sunday's final dimming and the way its structure changes deep inside. To picture this, imagine a campfire burning down. At first, bright flames represent active fusion. As the fuel runs low, glowing coals remain, slowly releasing stored heat. Over time, the coals cool and harden into ash. The Sunday will go through a similar process, though on a far greater scale and over much longer times. Even after the outer layers are gone, the white dwarf core will continue to glow faintly, a final reminder of the star that once sustained the solar system.